As a little bit of a deeper dive, we're going to take a look at the lists and sets. We'll come back to maps in another video, but right now I want to take a little bit deeper dive, not too much, but a little bit into the concepts around lists and sets. And then there'll be some videos to show them in use, particularly within the Java language for now. But there'll be other languages that, will be videos out there as well, maybe over time. Um, so the capabilities of a list are all the same as a collection, except since I know, like you can see our parking lot here, there's a numbered order to these positions. I can jump to any index or jump or remove or replace or anything along those lines. So, again, we have our parking lot here, and everybody has an assigned parking spot. So typically, if you go to a store, there is kind of a first come, first serve. Most people park as the closest parking spot to the store as they can. A few might choose to try, park further out because they're trying to protect their car, or they want the extra walk, whatever reason. But for the most part, they stack up front. That's the basic functionality of a list. They all stack up front. Um, Within this ordering that's set. So I just want to make sure we're really clear about the analogy, where the analogy breaks down on this. I can't, with a list, go park my car on the other side of the parking lot. I don't go park my car in slot 75. If I have 5 cars in the parking lot, they're in slots 0, 1, 2, 3, 4, or 1, 2, 3, 4, 5, depending on the language you're dealing in. But within the 5 cars that are there, I can remove the third car. I can replace the fourth car. I can insert at any point within that list. And that's the cool thing about the list is it allows me to be structures, be flexible inside of that. If I'm dealing with an array, then it means I have to move a bunch of data items around. So if I have an array of 5 items, I want to put something, insert something in the third item, then 3, 4, and 5 all get shifted up to 4, 5, and 6, and I add a new item inside of there. But from you as a user standpoint, you just say, boom, I make the command and I'm off and I'm running. So there's several different implementations, like the array list we were just talking about, that have different behaviors instead of there. So the array list stores things in an array, which gives you very, very fast access, but then manipulating the list can be slow. As I said, we have to shift everything else. Linked lists we'll learn a lot about through the data structures investigation, and they are really fast at inserting, ordering, and manipulating things, but they take a little bit more time to find things on the list, particularly big lists. Um, Vectors is another name for a list. In the Java world, it's the internal storage is used as an array, and it just kind of has this name. I really think it's important to talk about the vector here because it also takes us away from Java. C++ also has a vector in it, and there's many languages out there that have vectors that will help you to manage your data structures. So it's a common name that Java also calls lists here as well. And then we're also going to spend some time on the stack. So the stack really is a type of list, but it has a special behavior around pushing and popping that we'll talk about here in a second. So the idea of array list, as we said, there's an array inside, and we store some kind of object or number or string or date or whatever primitive or advanced type is going to be inside of that. They get wrapped in an array list, and really you kind of know what that data structure looks like. The interesting thing is just all the different rules and logic that would have you implement around inserting and moving stuff around. A lot of looping, a lot of shifting, or in some cases, just a quick direct lookup. You can think about it. If you want an item in an array, you say the array name and then some sort of bracket or parentheses depending on the language, and you give it the number and it jumps right to it. Same thing happens here, but everything else becomes more complicated. A linked list changes that where I'm actually using some dynamic storage allocation. It's sometimes called heap space. And in some languages, it's something that also requires direct memory manipulation. So Java, Python, those languages will manage the memory for you through ideas like garbage collection, which is where it automatically will delete things you don't need, where in other languages like C, you need to do that stuff yourself. But this combination of pointers back and forth across the node, and this is actually a doubly linked list in this case will help us to be able to quickly insert things. So you can see if I want to insert a node, I just simply change my arrows around in this structure. But if I want to find like the 7th item on the list, I have to walk down each link until I get to number 7. This is a data structure we'll spend quite a bit of time through this class. The stack, the best analogy I can start you with is exactly this picture I'm seeing here, this stack of books. So let's say you're reading that bottom book and you find something interesting and you want to go look it up in the other book, so that you see a reference to that and you say, well, let me understand this term better. So I go read this other book. I start reading the term and then there's another term I need to look up. So then I get that third book that's used there in the background. So before I start continue reading that bottom book inside of here, I want to understand the term that was in the second book, but then to understand that, I have to understand the term that's in the first book. And until I understand that term, I don't work back around. And this is a data structure. The stack is built for this sort of process. I kind of keep my memory of where I was while I do the next thing. And oh, wait, let me store that where I was while I go do the next thing. And we use this a lot in different aspects of computer science. It helps manage these little deep dives. They're not necessarily that familiar in other aspects of the real world, but if you do computer science a lot, they become quite normal, quite common. I mean, computer sciencey things like compilers and processor running and such like that. They don't show up, in my career, not in banking, insurance, and all that often, but there are other places where they really are quite useful and important. The set we talked a little bit about before. The important thing about the set, as we said, is it's one of a kind. So if you're a collector of stamps in this case, you do not want 2 of the 19 whatever stamp of this picture, whatever, from this country, whatever, whatever. Even if they're worth $100,000 a piece or $1 million a piece, you get one of them, and that's cool. The other one, I don't care about. I'm not going to buy it, or I'll sell it off right away, or whatever. But in my stamp collection, if I treat it as a collection, I have just a bunch of stuff inside of there, and it is what it is. If I treat it as a set, I only keep one of everything. So that's the idea behind a set. So really the main rule of a set is every time I add something in, I have to know, is it there already? I have to do a lot of searching through my materials, and that's where data structures are super important inside of a set. If I tried to implement a set as an array, every time I added something to the array, I would have to search every item in the array and compare it, and that's very slow. So sets typically have 2 common implementations, hash sets and tree sets. Hashing, we'll learn about, because it also goes with maps, is a very, very fast way of organizing data so I can search it in a hurry. Tree sets is also a fast way of searching data, not quite as efficient as hash sets, but it cuts the search space in half, essentially. And has the benefit that it orders things as it goes. The linked hash set is a Java special thing that, just to kind of show you, you don't have to sacrifice all behavior. So hash sets in general are just random bags of data. But I can do a linked hash set, which I can keep track of some order at the cost of additional memory, of additional lines of code that you have to execute in order to put things in. So that's a little bit of an introduction of these basic ones. I forgot that was the last slide here. There's a little introduction to the basic data types in a little bit more detail. Really, the next best thing to do is play with them. And that's what we're going to do a little bit more of. And I encourage you to do that, whether that's in your language you're coming from that you're comfortable with, or the language you might be learning as part of whatever data structures class you might be taking at any given time. Really, the idea behind these is pretty universal, but there can be some nuance in different languages. So, the classes I've taught around data structures before, and the reason why I'm being vague right here is, my primary is Java. I've also taught in C++, taught it with Python. And I mean, over time, the language might change even in classes I teach, but this information is timeless, and that's the point of this video, is to kind of capture some of these ideas separate from the language implementation, so you can realize that there are choices to be made within any of these data structures, the first of which is which one do you want to use and which one's the most valuable for your solution.